I want to talk a little bit about the last concept of this class, differentiability, and do a little bit of proofs and some examples related to that. I don't think we will have time, especially since I want to do it kind of leisurely this one and probably end a bit early, or try to end a bit early. So I won't. There are sample problems that are from the worksheet, but I maybe won't talk about them because that way we can end a little earlier and it's a little more peaceful. Okay. So outline, we'll first talk about these proofs. I will not talk about big O, little o notation. The notes do talk about that. It's just, let's not introduce a new thing in the last class. And then I don't think we'll have time for the problem outlines, but they're there. And yes, so if you just joined in, the notes that you're looking at, they are on Campus Wire. I upload them quite late, but if you just press that link, you'll get them. So what did we do on Wednesday? We introduced 3 different types of derivatives. We introduced partial derivatives, we introduced directional derivatives, and then we introduced the so-called full derivative that factors in all directions at the same time. Okay, and the partial derivative and directional derivative we can define as a limit. You take the difference of a function. Either you're going in the coordinate directions, so you're adding TEI, or you're going in the direction of some vector, so you're adding t times some vector. You're looking at the difference of the function divided by t. The full derivative is unfortunately defined in a little bit different way. It's defined by looking at the first order approximation. So fx plus h minus fx minus what ought to be the derivative. And we insist that this limit goes to 0. We say that the function is differentiable if there exists such a derivative. Often this is denoted df. Okay, and last time we mentioned some results, but we didn't say anything about how they're proven. So the first result that was that these 3 notions, 1, 2, 3, they fall in a hierarchy. 3, 2, 1. That the third one, having a differential or derivative, that's the strongest. After that, you have directional derivatives, and the weakest one is having just partial derivatives. And these weak notions, they don't need to be continuous, but the strongest notion does imply continuity. So the strongest notion is the real analog of having a derivative, whereas these two are some kind of artifact of working in higher dimensions. And this derivative map in the third part, it can be represented in a more familiar way. So if you are differentiable, then your linear map can be expressed as the gradient dot h, or the same thing as the directional derivative in the direction h of the function. So, and the gradient for us is nothing other than the vector of partial derivatives, partial 1 of f, partial 2 of f, etc., up to the nth partial derivative if you have a function from Rn to R, or some subset thereof. And we also observed, and we'll see it a bit below again, that the directional derivative is the same thing as the partial derivative if you go into the coordinate directions. So this was this lemma. But okay, so you have 3 different notions, but fortunately, sometimes they're all the same. There's no, you can get them all simultaneously. And the simple case is when you have partials, you take this weakest assumption, but you add something to it, namely continuity. These two together give you differentiability. And this is the test, except you can either just use the limit definition, or you can apply this test to prove differentiability. Usually this is the easiest thing. And this is what you did back in the day when you took 32A. On the final, your professor could ask you, prove that some function is differentiable while you computed its partials and then said that those were continuous. So you were really using this theorem even though you didn't know how to prove it. So these are the only results I will really talk about. The notes talk a little bit about other things like extreme value theorem and stuff like that. But I think the basic understanding of this concept is this theorem, okay, there's this technical lemma, and these two theorems. If you're going to only learn three things, I would say these things are the things you need a lot of the time.